Space itself can ripple like the surface of a pond. These are gravitational waves, cosmic vibrations born from the most violent events in existence. By the end of this journey, you will see the universe in an entirely new way, through the invisible ripples that sculpt reality itself. We will uncover how colliding black holes shake the fabric of space-time, and if we can truly listen to echoes from the dawn of time, what hidden force in the cosmos most captivates your imagination? Einstein's revolutionary theory revealed that space and time are woven into a single fabric called spacetime. This fabric is not a rigid stage but a dynamic entity that can bend, stretch, and even ripple. Those ripples are gravitational waves. Picture the most violent cosmic events, like two black holes locked in a final, spiraling dance. Their immense acceleration sends shockwaves through spacetime itself, much like a stone tossed into a still pond sends out expanding rings. These are not waves of light or sound, but literal distortions in the geometry of the universe. They travel outward at the ultimate speed limit, the speed of light, warping everything in their path. As a gravitational wave passes through you, it would subtly stretch your body in one direction while compressing it in another, an effect so incredibly tiny that detecting it seemed impossible for a century. This is why these waves are so revolutionary. They carry information about the most cataclysmic events, allowing us to observe a universe previously hidden from our telescopes, a cosmos seen not with light but through the very vibrations of reality. Albert Einstein himself first predicted these cosmic ripples back in 1916. His mind, working through the immense complexities of his general theory of relativity, revealed that the universe's fabric should indeed carry waves. Yet, in a stunning twist, the great physicist harbored deep doubts. He thought the effect would be so infinitesimally small, so utterly faint, that no instrument built by human hands could ever hope to sense it. Imagine predicting a whisper in a hurricane and believing it would remain forever silent. This was the scientific landscape for decades. Many in the community were skeptical, questioning whether these waves were even real or just a mathematical quirk of a brilliant but untested theory. It became a ghost in the machine of cosmology, a beautiful idea waiting for a world not yet ready to hear it. The quest to prove Einstein right and wrong about detectability would push technology to its absolute limits. It demanded a leap in precision so vast it was like measuring the distance to a nearby star and noticing if it shifted by the width of a single human hair. This decades-long journey to confirmation stands as a powerful testament to the human spirit of inquiry. It showcases the profound power of theoretical physics, its ability to map out the cosmos with pure thought and foresee wonders that would remain invisible for generations. That long-awaited whisper finally arrived on September 14, 2015. After a century of doubt and technological struggle, the Laser Interferometer Gravitational Wave Observatory, or LIGO, heard it. A specific, fleeting signal swept through the detectors. It was a sound that began low and quickly rose to a sudden, abrupt stop. Scientists named this event GW15094. What they were hearing was the final, frantic dance of two black holes. For over 1 billion years, these ripples in space-time had traveled across the cosmos. They told a story of two immense objects, each roughly 30 times the mass of our Sun, locked in a closing orbit. Their final moments were a cataclysm of unimaginable scale. In the last fraction of a second before they merged into one, they swung around each other at half the speed of light, releasing more power than all the stars in the observable universe combined. This energy erupted as a gravitational wave, the very signal LIGO captured. The detection was not just a single eureka moment, it was a profound confirmation. It proved that Einstein was spectacularly right about the existence of these waves, and wonderfully wrong about our ability to find them. More than that, it offered the first direct, undeniable evidence that binary black hole systems are not just theoretical possibilities. They are real, they exist out in the cosmos, and they collide. This single event did not just confirm a prediction. It ripped open a curtain, giving us an entirely new sense with which to perceive the universe. We were no longer just stargazers. We had become listeners to the silent, vibrating fabric of reality itself. The machine that heard this cosmic whisper is a masterpiece of engineering. It is called the Laser Interferometer Gravitational Wave Observatory, or LIGO. At its heart is a deceptively simple concept known as an interferometer. Imagine two incredibly long, empty tunnels arranged in a giant letter L. Each arm stretches for 4 kilometers, a distance so vast you cannot see from one end to the other. Inside, a single pure laser beam is split in two. One half travels down one arm, the other half journeys down the perpendicular arm. At the far ends, they hit near-perfect mirrors and bounce back to recombine. When the arms are exactly the same length, the returning light waves line up perfectly, creating a predictable pattern of light and dark. But when a gravitational wave passes through, it does something extraordinary. It subtly warps the very space the facility occupies. For an instant, one arm is stretched while the other is squeezed. This minuscule change, smaller than 1/10,000th of the diameter of a proton, means the laser beams no longer travel the same distance. They return out of sync and their recombined light pattern flickers. That tiny, almost impossible flicker is the signal. It is the universe's signature written in the geometry of spacetime itself. Of course, measuring a shift smaller than a subatomic particle on a human scale is a monumental challenge. The entire environment is a cacophony of noise. A distant ocean wave crashing on a shore, a truck rumbling on a highway miles away, even the constant quantum jitter of atoms in the mirrors themselves. All of these vibrations are vastly stronger than the signal LIGO is trying to find. To overcome this, scientists had to build the most advanced noise-canceling system on Earth. The mirrors are suspended by fine glass fibers and isolated from the ground by multiple layers of pendulums, creating a quiet oasis amidst the seismic rumble of the planet. The laser itself is amplified and purified to an almost unimaginable degree. It is a symphony of precision, where every possible source of interference is identified and silenced, allowing that one true cosmic vibration to finally be heard. This is not the work of a single nation. It is a global endeavor with twin detectors in the United States working in concert with others like Virgo in Italy. This collaboration is crucial as a real gravitational wave will sweep across the entire Earth, arriving at each detector with a slight delay, confirming its extraterrestrial origin. The ability to sense such an infinitesimal change is one of humanity's greatest technological achievements. It transforms empty space into the most sensitive musical instrument ever conceived, an instrument tuned not to sound but to the silent ripples of gravity. These cosmic messengers are born from the most violent and energetic processes the universe can muster. The first signals we heard came from colliding black holes, but the sources are as varied as the cosmos itself. Consider a binary star system, two dense remnants like neutron stars locked in a tight orbit. As they spiral closer over millions of years, they stir the fabric of space-time, sending out a constant, faint hum of gravitational waves. This is the universe's background music, a steady rhythm of orbital motion. Then there are the stellar explosions, supernova. When a massive star collapses, its core can implode with such violent asymmetry that it rings space-time like a bell struck by a hammer, creating a sharp, powerful burst of waves. But the most extreme events, the ones that produce the loudest, most detectable signals, involve the most massive objects undergoing the most dramatic acceleration. The intensity of a gravitational wave is directly tied to the masses involved and how quickly they are moving. Two stellar mass black holes merging create a clear chirp. But imagine the signal from two supermassive black holes. each with the mass of billions of suns crashing together in the heart of a galaxy. That event would unleash a tsunami in space-time, a low-frequency rumble of immense power that would wash over entire star systems. Each type of event leaves a unique fingerprint in the waveform, a specific pattern of rising frequency and amplitude that tells astronomers exactly what kind of cosmic drama unfolded. By reading these vibrations, we gain a direct line of sight into the most cataclysmic processes that shape our universe, processes that are often completely invisible to traditional telescopes. That sound, the one first heard in 2015, is known among scientists as the chirp. It is a cosmic whistle that starts as a low rumble and rapidly rises in both pitch and volume before cutting off abruptly. This specific audio signature is not a random noise. It is the direct translation of a death spiral. As two massive objects like black holes orbit each other, they lose energy by radiating gravitational waves. This energy loss pulls them closer together, forcing them to orbit faster and faster in a runaway process. The frequency of the waves they emit rises accordingly, and the amplitude or the loudness swells as the objects get nearer and their acceleration becomes more violent. The resulting sound file is that unmistakable chirp, a perfect audio representation of an inevitable collision. It is the sound of space-time itself being violently stirred. To make this abstract concept relatable, think of a small marble rolling around the inner rim of a large bowl. At first, it moves slowly with a low, lazy rumble. But as it loses energy to friction, it spirals down into a tighter, faster orbit, its whirring sound rising in pitch and intensity until it suddenly stops at the bottom. The gravitational wave chirp is that same principle, but played out on a cosmic scale with unimaginable forces. This pattern is so distinctive that it acts like a fingerprint for astronomers. By reading the precise shape of the chirp, the steepness of its rise and its final frequency, scientists can decipher the nature of the objects that created it. They can determine their masses, their distances, and even their spins. A merger of two neutron stars, for instance, produces a different chirp than a black hole collision, often with a different duration and a higher maximum frequency. This allows us to not just hear the universe, but to understand the specific drama unfolding in the darkness. Each chirp is a story, a data-rich message from the depths of space, telling us exactly what kind of monsters are dancing in the void. The chirp is the sound of a black hole merger, one of the most powerful events since the Big Bang. When two black holes are caught in their final embrace, they release more energy than anything else we can observe. In the last few seconds before they become one, an amount of energy equivalent to several times the mass of our own sun is converted directly into gravitational waves. This is not energy released as light or heat, but pure, raw vibration in the fabric of space-time. The entire process unfolds in three distinct acts, a cosmic play written in the language of gravity. It begins with the in-spiral, the long, slow dance we hear as the rising chirp. The two black holes orbit each other faster and faster, whipping around at relativistic speeds and shedding orbital energy with every pass. This dance cannot last. It culminates in the merger itself, a violent, chaotic collision where the two singularities become one. This moment is the peak of the gravitational wave signal, a final, crashing note. But the event does not end there. The newly formed single black hole is born misshapen and wobbly like a struck bell. It must settle into its final, smooth shape, and it does so through a process called ringdown. It shakes off its imperfections, emitting a final, fading series of gravitational waves, a quiet hum that smooths out into silence. This entire sequence, from in-spiral to merger to ringdown, is a treasure trove for scientists. The specific frequencies and amplitudes within the signal act as a cosmic fingerprint, revealing the precise masses of the original black holes and the spin of the final object. By listening to the ring down, we can even test if the resulting object truly behaves as Einstein's theory predicts a black hole should. Each merger is a unique experiment, providing a direct window into the formation history and fundamental properties of these dark giants, all without a single photon of light. While black hole mergers are powerful, they are fundamentally dark events. Neutron star collisions, however, are the cosmic equivalent of a grand fireworks display, illuminating the universe in multiple ways. When two of these incredibly dense stellar corpses spiral together, they do not just create gravitational waves, they also unleash a spectacular show of light from gamma rays to visible glows. This dual signal is what makes them so extraordinary. A neutron star is the collapsed core of a massive star, so dense that a single teaspoon of its material would weigh billions of tons on Earth. When two of them orbit each other, they emit a steady stream of gravitational waves, just like black holes slowly decaying their orbit. Their final collision is a cataclysm of a different order. The resulting explosion, known as a kilonova, is a forge of creation. In the intense heat and pressure, neutrons are blasted into atomic nuclei, building up heavy elements in a frantic process. It is here, in the heart of this violent merger, that the universe forges the gold in your jewelry and the platinum in catalytic converters. These precious metals are then scattered across space by the explosive force, eventually seeding future generations of stars and planets. This discovery fundamentally changed our understanding of the cosmos. We now know that the origins of the heaviest elements are not in the quiet deaths of stars, but in their most violent, explosive collisions. The first observation of this in August of 2017 was a landmark event. The LIGO and Virgo detectors picked up the gravitational wave chirp of two neutron stars merging. Crucially, just 2 seconds later, space telescopes detected a powerful burst of gamma rays from the same patch of sky. This was the trigger for a global astronomical campaign. Dozens of telescopes across every wavelength of light swiveled to observe the aftermath. They witnessed the kilonova's evolving glow, a direct confirmation of the element-forming process. This coordinated effort, known as multi-messenger astronomy, was like having both ears to hear the spacetime vibrations and eyes to see the resulting fire. It allows us to get a complete picture of a single cosmic event, piecing together the story from the gravity that shapes it to the light it emits. Each neutron star collision we observe is not just a source of waves, but a factory for the very building blocks of our material world, a testament to the fact that we are all truly made of stardust. But the death of a single star can also send its own unique shiver through the cosmos. When a massive star exhausts its nuclear fuel, its core collapses in a cataclysmic event known as a supernova. While the outer layers are blasted into space in a brilliant flash, the inner drama is a chaotic, violent process that can wring spacetime itself. Not every supernova creates a detectable gravitational wave signal. The key lies in asymmetry. If the collapse is perfectly spherical, the gravitational effects cancel out, but nature is rarely so orderly. Imagine a colossal star spinning rapidly as it dies. Its core implodes, and if this collapse is lopsided, or if the newborn neutron star at its heart is born with a powerful wobble, it acts like a massive, unbalanced washing machine drum. This violent, jerking motion throws powerful ripples into the fabric of the universe. These are not the clean, predictable chirps of a binary merger. They are short, complex bursts, a frantic stutter of gravitational energy that encodes the secret physics of the explosion itself. Detecting these signals is one of the next great challenges. They are buried in a storm of noise, and their unpredictable shape makes them incredibly difficult to tease out from the random fluctuations of our detectors. Yet the scientific reward for catching one would be immense. It would be like placing a microphone inside the heart of an exploding star. For the first time, we could listen to the birth cries of a neutron star or a black hole. We could understand the exact mechanisms that cause a star to tear itself apart and learn what determines whether its remnant will be a pulsar, a magnetar, or a dark void. Each supernova burst would be a direct transmission from the moment of creation, revealing the violent forces that forge the elements and scatter the seeds for new worlds. While supernova burst and black holes crash, another, more subtle song plays on a near-infinite loop. It is the persistent hum of a spinning neutron star. These cosmic lighthouses, known as pulsars, can spin hundreds of times every second, flashing beams of radiation with metronome-like precision. If such a star possesses even a tiny bump on its surface, a microscopic mountain just a few centimeters high, its rapid rotation makes it an imperfect sphere. This minuscule deformity, whirling around at incredible speeds, stirs the fabric of spacetime continuously. It does not create a dramatic chirp, but a steady, almost pure tone of gravitational waves, a single note held for eons. This is the universe's background hum, a signal that is always there, waiting to be heard. Detecting it, however, is a monumental challenge. The signal from a single pulsar is vastly weaker than the cataclysmic blast from a black hole merger. It is not a shout, but a whisper that never stops. To have any hope of finding it, scientists must listen to the same patch of sky for months or even years, patiently accumulating data and sifting through the noise for that faint, persistent tone. This is not the work of a single observation, but a long-term vigil. Why go to such extraordinary lengths for such a quiet signal? Because this continuous wave holds secrets that a merger's violent crash cannot reveal. By measuring the precise frequency and strength of this hum, we can peer into the heart of the neutron star itself. We can learn about the nature of the ultra-dense matter it is made of, a substance so compressed that it exists in states impossible to create in any laboratory on Earth. Is the core a soup of free quarks or a solid crystalline mass? The steady gravitational tone acts like a cosmic stethoscope, allowing us to feel the heartbeat of these dead stars and finally understand what lies beneath their impenetrable surfaces. Beyond the isolated chirps and bursts lies a far more profound murmur. It is a random, chaotic sea of vibrations known as the stochastic gravitational wave background. This is not the signal from a single event, but the collective hum of every unresolved gravitational wave source across the entire cosmos, all overlapping into a persistent, low hiss. Think of it as the universe's equivalent of the cosmic microwave background radiation, that ancient afterglow of the Big Bang we see as light. But this is the background hiss of gravity itself, a fossil imprint of the universe's most violent history. Its sources are as mysterious as they are numerous. It could be the combined rumble from millions upon millions of binary black hole systems too distant for our detectors to pick out individually, a cosmic choir singing in unison. It might be generated by hypothetical cosmic strings, fantastically thin defects in space-time left over from the universe's birth, vibrating like incredibly long violin strings. Or, most tantalizingly, this background hum could carry echoes from the universe's first moments after the Big Bang, a period of rapid expansion called inflation. During this time, the very fabric of spacetime would have been quantum foam, bubbling and shaking, potentially creating gravitational waves that have been resonating for over 13 billion years. Detecting this faint signal is one of the most difficult challenges in modern physics. Our current observatories like LIGO are not sensitive to these ultra-low frequency waves. Instead, scientists are turning the entire galaxy into a detector using pulsar timing arrays. They monitor the incredibly regular flashes from a network of millisecond pulsars, the universe's most precise natural clocks. As a stochastic gravitational wave passes through, it minutely stretches and compresses the space between us and these pulsars, causing their ticks to arrive a fraction of a second early or late. By carefully watching for a correlated pattern of these tiny timing shifts across many pulsars, astronomers are hunting for the signature of this cosmic hum. Finding it would open a window into the earliest epochs of time, allowing us to listen to the universe's birth cries in a way no telescope ever could. The most ancient whispers in the cosmos are not from black holes or neutron stars. They come from the very beginning of everything. These are primordial gravitational waves, theorized to have been generated in the universe's first fleeting moments, a trillionth of a second after the Big Bang. This was a period of unimaginable violence called cosmic inflation, when the entire universe is thought to have expanded faster than the speed of light, blowing up from a subatomic speck to a macroscopic size in an instant. Such a violent, rapid stretching of spacetime itself would have sent powerful tremors rippling through the newborn universe, vibrations that have been traveling for over 13 billion years. These waves are not from colliding objects, but from the fabric of reality shaking itself into existence. They carry a unique, random pattern, a chaotic hiss that would imprint itself on the oldest light in the universe. Detecting this signal is the ultimate goal for many cosmologists, for it would be the most direct evidence we could ever obtain for the theory of inflation. It would be like finding a fossil from the first second of time, a snapshot of the universe in its infancy. The challenge, however, is immense. These primordial waves are predicted to have extremely long wavelengths, far longer than what ground-based detectors like LIGO can sense. They have been stretched and diluted by the expansion of the universe itself, fading into a near-silent hum. To find them, scientists look for their indirect signature in the cosmic microwave background, the afterglow of the Big Bang. As these ancient gravitational waves passed through the hot, dense plasma of the early universe, they would have subtly polarized the light, leaving a distinct swirling pattern known as a B-mode polarization. Finding this specific fingerprint in the sky is like finding a single, faded watermark on a document from the dawn of time. While tentative claims have been made, a definitive detection remains elusive, one of the greatest prizes in modern science. To finally confirm the existence of primordial gravitational waves would do more than just validate a theory. It would open a window to a time before the first stars, before the first atoms, allowing us to probe the very moment of creation and answer the most profound question of all: how did the universe begin? The universe sings its gravitational song not in a single note, but across a vast spectrum of frequencies. Just as light spans from long radio waves to short gamma rays, gravitational waves cover an immense range of pitches, each revealing a different kind of cosmic drama. At the very lowest end of this spectrum are the ultra-low frequency waves. These are the deep, rumbling bass notes of the cosmos, with wavelengths so long it can take years or even decades for a single wave to pass by. You cannot hear these with LIGO, their vibrations are too slow and stretched out. Instead, we detect them by watching the universe's most precise natural clocks, millisecond pulsars. The sources of these ultra-low rumbles are the most colossal objects in existence, like pairs of supermassive black holes, each weighing billions of suns, slowly circling each other in the hearts of distant galaxies. Their stately, million-year-long orbital dance generates this persistent, low hum that permeates all of space. Moving up the scale, we find the low-frequency band. This is the territory of future space-based observatories. Here, you would hear the mergers of smaller supermassive black holes and the intricate dances of compact stars as they spiral into massive black holes. These waves have frequencies much higher than the cosmic rumble, but still too low for ground-based detectors. Then we reach the high-frequency window, the domain of LIGO and Virgo. This is where the universe's most violent and sudden crashes are heard. The chirps from colliding stellar mass black holes and neutron stars reside here, their frequencies soaring to hundreds of cycles per second in their final, frantic moments. It is in this specific sonic range that the fabric of spacetime is plucked most sharply and loudly by these catastrophic collisions. Each frequency band acts like a different radio station, tuned to a specific class of cosmic events. By learning to listen across this entire gravitational spectrum, we are no longer limited to one type of sound. We can hear the deep bass of galactic cores, the mid-range tones of stellar encounters, and the high-pitched shrieks of final collisions, assembling a complete and vibrant symphony of the dynamic, violent universe. Einstein's theory insisted these ripples must race across the cosmos at the ultimate speed limit, the speed of light. For a century, this was a central, untested pillar of his theory. Then, in August of 2017, we got our chance for a direct measurement. The LIGO and Virgo detectors recorded the distinctive chirp of two neutron stars colliding. Just 1.7 seconds later, space telescopes observed a brilliant flash of gamma rays bursting from the exact same region of sky. This was the perfect cosmic experiment. Both the gravitational waves and the light were born from the same cataclysmic event, and they had been traveling for over 100 million years to reach us. If they arrived essentially at the same time, it meant they had traveled at the same speed. The timing was precise beyond belief. The data showed that gravitational waves and light move through the vacuum of space with a velocity differing by no more than 1 part in a million billion. This incredible confirmation was a monumental victory for general relativity, but the implications run even deeper. What if they had not arrived together? Even a tiny delay could have shattered our understanding of gravity. It would have been a direct hint of new physics, perhaps evidence of extra hidden dimensions of space that the waves had to traverse, or a sign that the graviton, the hypothetical particle of gravity, has a slight mass. The fact that they matched so perfectly means our current model of spacetime is astonishingly accurate. Every new cosmic crash we observe is not just a discovery, it is a stringent test of the universe's most fundamental rules, measured with a precision that was once the stuff of pure fantasy. The sheer power carried by these silent ripples is almost beyond human comprehension. During that first detected black hole merger, the energy released in gravitational waves for a fleeting fraction of a second outstripped the combined light output of every single star in the observable universe. This was not a slow burn, but a catastrophic blast of pure vibrational energy, a storm in the fabric of reality itself. That immense power comes from a direct and startling conversion. As two massive bodies orbit one another, they are constantly losing orbital energy to these emitted waves. Think of it as a cosmic tax paid in the currency of spacetime vibrations. This energy loss has a direct physical consequence. It forces the orbiting objects, whether they are black holes or neutron stars, to spiral inward toward their inevitable collision. Their dance grows tighter, faster, and more frantic as they bleed energy into the universe, a process that can continue for millions of years before the final, dramatic chirp. This constant drain of gravitational wave energy is a fundamental force shaping the cosmos. It acts as a cosmic sculptor, particularly within the dense cores of galaxies where supermassive black hole binaries are thought to reside. The energy they radiate away as waves over eons helps to stabilize these galactic centers, preventing stellar systems from being flung into the void and influencing the growth of the black holes themselves. This energy, now measurable, becomes part of the universe's budget, a hidden but potent force that has been quietly choreographing the evolution of the largest structures in existence, all through the faintest of tremors. Gravitational waves do not simply stretch and squeeze space in a single, uniform way. They arrive with a specific orientation, a hidden pattern in their distortion known as polarization. Just as light waves can be polarized, filtering their direction of vibration, gravitational waves exhibit two distinct polarization states, named plus and cross for the shapes they imprint on spacetime. Imagine a perfect, still circle of floating dust particles in space. When a plus polarized wave passes through, it will first stretch the circle vertically while squeezing it horizontally, turning it into a tall, thin oval. A moment later, it reverses, squeezing it vertically and stretching it horizontally into a wide, flat oval. It continuously oscillates between these two states. The cross-polarization does the very same thing but rotated by 45 degrees. It stretches and squeezes along the diagonal axis, distorting the circle into a diamond shape that pivots back and forth. This is why detectors like LIGO are built in their iconic L shape. The two perpendicular arms are perfectly positioned to sense the difference between these two polarizations. As a wave passes, one arm might be stretched while the other is squeezed, creating the telltale interference signal. The specific mix of plus and cross polarizations in a signal is a crucial piece of information. It acts like a cosmic compass, telling us about the orientation of the source out in the depths of space. Was the binary system spinning face onto us, or was it tilted edge on? The polarization pattern holds the answer. Furthermore, this characteristic signature provides a powerful test of Einstein's theory of general relativity. Some alternative theories of gravity predict the existence of more than just these two polarization states. They suggest additional modes, perhaps ones that would make space breathe by expanding and contracting in all directions simultaneously. So far, every gravitational wave we have detected perfectly matches the plus and cross pattern predicted by Einstein. Each new event is another vote of confidence, another checkmark confirming that our fundamental understanding of gravity, at least in its most extreme regimes, appears to be correct. Yet this cosmic listening post is not a solitary instrument. The faint tremor of a gravitational wave is so subtle that a single detector cannot fully trust its own senses. This is why the hunt is a global effort, a coordinated network of ears straining to hear the same cosmic whisper. Alongside the twin LIGO detectors in the United States, other observatories join the chorus. There is Virgo, located in the rolling Italian countryside near Pisa, and Cagra, nestled deep within a mine in Japan. Each of these facilities operates on the same fundamental principle as LIGO, but their geographical separation is the key to unlocking the universe's secrets. When a gravitational wave sweeps through the Earth, it does not arrive everywhere at the same instant. It might hit the Livingston detector in Louisiana, then a few milliseconds later, be registered by Virgo in Italy, and finally by Cagra in Japan. This tiny time delay is everything. By comparing the precise moment the signal arrives at each location, scientists can perform a form of cosmic triangulation. It is like hearing a clap of thunder and using the slight difference in when the sound reaches your left and right ears to pinpoint the location of the lightning strike. This network dramatically reduces the chance of a false alarm, as a local vibration or a glitch in one detector will not appear in the others. But more importantly, it allows researchers to narrow down the sky position of the event from a vast, fuzzy patch encompassing thousands of galaxies to a much smaller, more manageable area of the sky. This precise localization is the crucial first step for our telescopes. Without it, astronomers would be staring into an immense cosmic haystack with no idea where to find the needle. The international collaboration between LIGO, Virgo, and Cagra transforms a curious signal into a targeted celestial address, enabling the global astronomical community to swing into action and witness the aftermath of these colossal explosions in light, X-rays, and radio waves. This is modern astrophysics in action, a truly global endeavor where discoveries are made not by a single nation, but by a united planet listening to the subtle vibrations of the cosmos. This new sense of hearing the cosmos fundamentally rewrites the rules of observation. For centuries, astronomy meant collecting light from the visible glow of stars to the invisible whispers of radio and X-rays. This is electromagnetic astronomy, and it relies on photons traveling across the universe to tell their stories. But light can be blocked, absorbed, or scattered by cosmic dust and gas. It cannot escape the event horizon of a black hole, and it struggles to pierce the densest regions of stellar formation. Gravitational wave astronomy operates on an entirely different principle. It is not observing the universe with light but feeling its vibrations. These waves are a direct probe of gravity itself, the very force that sculpts the cosmos on its largest scales. They pass through matter almost completely unimpeded, flowing through dust clouds, stars, and even entire galaxies as if they were not even there. This allows them to carry information from places light can never escape, most notably from the dark, silent abyss surrounding black holes. A black hole merger is invisible to telescopes, but it is a roaring symphony for gravitational wave detectors. This is not a replacement for traditional astronomy, but a powerful complement. It is like having been deaf in a world of vibrant color and suddenly gaining the ability to hear. The true power emerges when we combine our senses. The landmark detection of two neutron stars merging in 2017 was the perfect example of this multi-messenger synergy. The gravitational wave signal told us the precise masses of the objects and the nature of their violent dance. The subsequent flash of light across the electromagnetic spectrum revealed the fiery aftermath, the creation of heavy elements, and the properties of the expanding debris. One sense alone gave a partial picture. Together, they told the complete, breathtaking story of a cosmic collision, from its initial spacetime ripples to its luminous, element-forging finale. This partnership allows us to see the unseen and hear the silent, opening a new chapter where we can fully witness the universe's most dramatic events. Among the chorus of cosmic collisions, a curious silence echoes from a specific mass range. Scientists call this the mass gap, a puzzling void in the populations of dead stars. On one side, we have neutron stars, the densest objects that can resist collapsing into a black hole, with a theoretical upper limit around 2.2 times the mass of our Sun. On the other side, we have the lightest black holes we have observed, starting at around 5 solar masses. This leaves a mysterious desert between roughly 2.2 and 5 solar masses, a gap where very few compact objects seem to exist. It is as if the universe has a rule against creating stellar corpses of a certain weight. Why would nature avoid this specific range? One leading theory points to the supernova explosion that creates these objects. The death of a massive star is a complex, violent process. It is possible that the physics of a core collapse supernova simply cannot produce a stable remnant with a mass neatly in this gap. Perhaps a star that would leave a 3 solar mass remnant instead completely blows itself apart, leaving nothing behind. Or the mechanism might consistently produce either a neutron star below the gap or kick it with enough force to collapse directly into a black hole above the gap, neatly skipping the middle ground. Another possibility is that our observations are simply biased. Before gravitational wave astronomy, we found black holes by the light they emitted from consuming companion stars, a method that might miss quieter, isolated objects in this mass range. The gap, then, might not be a true emptiness but a shadow in our data. Every new gravitational wave detection is a census of the dark population of compact objects. With each chirp, we are mapping the demographics of the dead. A single, clear detection of an object firmly within this mass gap would send shockwaves through astrophysics. It would force us to reconsider our models of stellar death and collapse. Did it form directly from a star, challenging our supernova theories, or could it be the product of a previous merger, two lighter neutron stars combining to create an object that is neither a neutron star nor a classic black hole? Finding such an object would not just fill a blank spot on a chart. It would unlock new secrets about the final moments of massive stars and the ultimate fate of matter under extreme pressure. Sometimes the universe itself becomes a cosmic catapult. When two black holes spiral together and merge, the resulting object can be kicked away at an astonishing speed, a recoil from the violent emission of gravitational waves. This is not a gentle nudge, but a powerful thrust that can send a black hole with the mass of dozens of suns hurtling through space. The key to this incredible force is asymmetry. For the kick to occur, the merger cannot be perfectly clean. The most common cause is a mismatch in the spins of the two original black holes. If their axes of rotation are not aligned with their orbital dance, the final moments of the merger become a chaotic, lopsided event. Imagine two figure skaters spinning independently as they clutch each other in a final, frantic embrace. If their spins are misaligned, their final union is a messy, off-balance collision. In that last violent instant, more gravitational waves are shot out in one direction than the other. Just as a rocket moves forward by expelling exhaust backward, the new black hole recoils from this lopsided blast of energy. The resulting kick velocities can be staggering. Scientists have calculated that under the right conditions, a newborn black hole can be ejected at over 5,000 kilometers per second. That is fast enough to cross the entire United States in the blink of an eye. At such speeds, the black hole would easily escape the gravitational pull of its host galaxy, becoming a rogue wanderer in the immense darkness between galaxies. This dramatic process has profound implications. It means that the central black holes we observe in galaxies today are not necessarily the original inhabitants. A galaxy could lose its central monster to such a kick, leaving its core strangely empty. Alternatively, a wandering black hole ejected from another galaxy could be captured, becoming a new gravitational anchor. This gravitational recoil shapes the population of black holes we see, scattering them across the cosmos and influencing the evolution of galaxies themselves. These invisible, high-speed ejections are a reminder that even the most massive objects are not immune to the violent, unpredictable forces they help to create. Even a black hole's quiet feast can send ripples through spacetime. When a star drifts too close to a supermassive black hole, it encounters a force so extreme it is literally pulled apart. The black hole's gravity is so much stronger on the side of the star nearest to it that it stretches the star into a long, thin stream of gas, a cosmic noodling event known as a tidal disruption. This is not a clean, instantaneous destruction. It is a messy, chaotic process. As the star is shredded, its material forms a vast, swirling disk of superheated debris around the black hole, shining brilliantly across the electromagnetic spectrum. But within this luminous chaos, there is also a hidden gravitational story. The sudden, asymmetric infall of all that stellar matter, the violent sloshing and churning as it is consumed, gives the fabric of spacetime a sharp, complex jolt. Unlike the clean, predictable chirp of two black holes merging, the gravitational wave signal from a tidal disruption event would be a brief, tangled burst. It would not have the smooth, rising pattern of an in-spiral. Instead, it would be a staccato blast of vibrations, a direct audio recording of the star's destruction and the chaotic feast that follows. This messy signal is actually packed with valuable information. By untangling its complex waveform, scientists could learn two critical things. First, they could measure the spin of the supermassive black hole itself. The way the stellar debris falls in is deeply influenced by how fast the black hole is rotating. Second, they could probe the internal structure of the star that was torn apart. How a star of a certain mass and age resists being pulled apart tells us about its density and composition. These events are rare, occurring only once every 10,000 years or so in a typical galaxy, making them a precious and violent laboratory for studying both the most massive black holes and the ordinary stars that dare to venture too close. Just as light can be bent by a cosmic lens, so too can these ripples in spacetime. When a gravitational wave travels across the universe, its path is not always a straight line. If it passes near a truly massive object like a galaxy cluster or a solitary supermassive black hole, the immense gravity of that object acts like a lens. It warps the fabric of spacetime around it, and the gravitational wave traveling through that warped fabric has its own trajectory bent. This phenomenon is called gravitational lensing, and for waves it creates extraordinary possibilities. A single cosmic crash could appear to us not once but multiple times. the lensing object can split the wave's path, creating two or more copies of the same signal that arrive at our detectors at different times. Imagine hearing an echo of a black hole merger and then, days or even weeks later, hearing that exact same chirp again, a perfect cosmic replay. The signal could also be amplified, its quiet whisper boosted into a clearer shout as the lens focuses the wave's energy toward us. Detecting these lensed events is a new frontier. The telltale sign would be finding two or more gravitational wave events with identical waveforms, the same cosmic fingerprint, but originating from the exact same patch of sky and separated by a predictable delay. Why would we go to such lengths to find these cosmic echoes? Because a lensed gravitational wave is more than just a signal, it is a powerful new tool for cosmology. By measuring the time delay between the multiple images, scientists can perform a unique kind of cosmic geometry. They can triangulate the distances involved with incredible precision, providing an independent check on the expansion rate of the universe. Even more profoundly, since the lensing is caused by gravity, it is sensitive to all matter, including the invisible dark matter that dominates the cosmos. By analyzing how these waves are bent, we could finally map the distribution of this mysterious substance, tracing the unseen scaffolding of the universe itself through the subtle warping of its most fundamental vibrations. The silent chirp of colliding neutron stars does more than just announce a cosmic catastrophe. It also acts as a perfect cosmic ruler, a tool astronomers call a standard siren. When two neutron stars spiral together and merge, the gravitational wave signal they emit carries a direct, built-in measurement of their distance. The amplitude of the waves, their loudness, tells us precisely how far away the event occurred. By then locating the host galaxy with optical telescopes and measuring its redshift, its speed of recession, we can calculate the universe's expansion rate, a number known as the Hubble constant. This is one of the most critical numbers in all of cosmology, the very speedometer of our expanding cosmos. Yet this new method has thrown a wrench into our understanding. The expansion rate measured by these gravitational wave sirens does not perfectly match the value derived from the ancient light of the cosmic microwave background, the afterglow of the Big Bang. There is a persistent, stubborn tension between the two. One method looks at the local, modern universe with standard sirens, while the other peers back to the universe's infancy. They should agree, but they do not. This is not a small statistical fluke. It is a discrepancy that has withstood years of improved measurements and analysis. So what does this mean? This Hubble constant tension could be the most exciting hint of new physics we have encountered in decades. It might be a sign that our understanding of dark energy is incomplete, that its strength has changed over the lifetime of the universe. Perhaps there existed an unknown, exotic particle in the early cosmos that altered its evolution. Or, most profoundly, it could indicate a flaw in our standard model of cosmology itself, forcing us to reconsider the very ingredients and history of everything. Each new neutron star merger we detect with both gravitational waves and light sharpens this measurement. With every standard siren we hear, we are not just witnessing a distant collision. We are gathering the data that might one day crack open our model of the universe and reveal a deeper, more complete reality. But one of the most exotic sources of gravitational waves is entirely theoretical. The concept is called a cosmic string. Picture a flaw in the universe's fabric, a one-dimensional crack in reality left over from its fiery birth. These hypothetical strings would be unimaginably thin, yet they could stretch across the entire cosmos, possessing immense mass and tension. If they exist, they would be the ultimate cosmic fault lines, remnants of a phase transition in the early universe when the fundamental forces split apart. The gravitational waves from such an object would be unlike any chirp or burst from colliding bodies. A cosmic string oscillating through space, writhing like a snapped whip, would send out a steady stream of continuous gravitational waves, a pure, constant tone. Even more dramatically, if two strings were to cross or a loop of string were to snap, the event would release a sharp, powerful burst of gravitational radiation, a single, explosive crack in spacetime. These signals would be unmistakable, carrying a unique fingerprint that would point directly to their bizarre origin. The search for these waves is, in essence, a hunt for the echoes of the universe's first moments. Detecting a signal from a cosmic string would be a direct window into physics at energy scales 1 trillion times higher than anything we can achieve in our particle colliders. It would confirm a key prediction of many grand unified theories and illuminate the conditions of the cosmos when it was less than a second old. Every time our detectors listen to the silent universe, they are not just waiting for black holes to crash. They are listening for the faint, telltale hum or the sudden snap of a cosmic string, a vibration that would reveal the very architecture of spacetime and rewrite our understanding of cosmic history. Even after the cosmic ripples fade, they leave a permanent scar on the universe. This strange effect is known as gravitational wave memory. When a powerful gravitational wave, like that from a black hole merger, passes through a region of space, it does not just stretch and squeeze things temporarily. It can actually cause a permanent, irreversible deformation in the fabric of spacetime itself. Imagine a grid of floating markers in space, set perfectly equidistant from one another. As the wave passes, they oscillate back and forth, but once the wave is gone, they do not return to their original positions. The grid is left slightly, yet permanently, distorted. One set of markers will be forever farther apart than they were before, while another set will be closer together. This is not a temporary vibration, but a lasting change written into the geometry of reality, a permanent dent caused by the most violent events in the cosmos. This prediction comes straight from the heart of Einstein's general relativity, specifically from its nonlinear nature. In our everyday world, forces usually act in a simple, linear way. Push on a spring and it compresses a certain amount, push twice as hard and it compresses twice as much, but gravity in Einstein's theory is different. It is nonlinear, meaning it acts upon itself. The gravitational field generated by masses actually has its own gravity. When two black holes merge, the gravitational waves they emit are not just simple messengers. They themselves carry energy, and that energy creates its own gravitational pull. It is this self-interaction, this gravity of gravity, that is responsible for the memory effect. The passing wave permanently rearranges the spacetime in its wake. Detecting this tiny, permanent shift is one of the most difficult challenges in modern physics. The change is incredibly small, even by the already minuscule standards of gravitational wave science. Our current observatories like LIGO are simply not sensitive enough to pick out this faint, permanent drift from the much larger, temporary oscillation of the main wave signal. It is like trying to measure the permanent, microscopic widening of a valley after a massive earthquake has subsided, while you are still being thrown about by the aftershocks. Scientists are devising new strategies, looking for the cumulative effect of many such events over time, or planning for future, ultra-sensitive detectors in space. Successfully observing gravitational wave memory would be a monumental achievement. It would provide the most direct evidence yet for the nonlinear nature of gravity, a cornerstone of general relativity that has never been tested in this specific, fundamental way. It would prove that the universe does not just vibrate, it remembers. Every cosmic crash would leave an eternal, silent signature on the cosmos, a fossil of violence etched into the fabric of space and time. The silent aftermath of a black hole collision holds a profound secret about the nature of the objects themselves. This is where we test one of the most elegant ideas in physics, the no-hair theorem. This theorem suggests that black holes are the ultimate simpletons in the cosmos. No matter how complex the star that formed them or what they have consumed since, a black hole can be completely described by just three numbers: its mass, its spin, and its electric charge. It has no other distinguishing features, no hair, no bumps, no memories of its past. All other information is lost forever behind the event horizon. This stunning simplicity means that any two black holes with the same mass, spin, and charge are absolutely identical. They are perfect cosmic clones, but how can we possibly verify such a bold claim from billions of light years away? The answer lies in the final moments of a gravitational wave signal in the ring down. After the violent merger, the newborn black hole is not smooth. It is misshapen and wobbly, vibrating like a struck bell. These vibrations are not random. They are specific, damped oscillations known as quasi-normal modes. The frequencies and rates at which these vibrations fade away are determined exclusively by the black hole's final mass and spin, according to Einstein's equations. It is a direct prediction of the no-hair theorem. By carefully listening to the ring-down hum in our detectors and measuring its precise tone and decay, we can check if the newly formed black hole truly behaves as a pure Einsteinian object should. Does its vibration pattern match the one predicted for its specific mass and spin? Every time the data aligns perfectly, it is a powerful confirmation that the no-hair theorem holds. A mismatch, however, would be revolutionary. It would suggest that black holes are more complex than we thought, that they might have hidden structures or perhaps even a hard surface, challenging the very foundations of general relativity and our understanding of where information goes when it falls in. Each ring down we analyze is not just the end of a signal, it is a direct interrogation of a cosmic singularity. The most ancient whispers in the cosmos are not from black holes or neutron stars. They come from the very beginning of everything. These are primordial gravitational waves, theorized to have been generated in the universe's first fleeting moments, a trillionth of a second after the Big Bang. This was a period of unimaginable violence called cosmic inflation, when the entire universe is thought to have expanded faster than the speed of light, blowing up from a subatomic speck to a macroscopic size in an instant. Such a violent, rapid stretching of spacetime itself would have sent powerful tremors rippling through the newborn universe, vibrations that have been traveling for over 13 billion years. These waves are not from colliding objects, but from the fabric of reality shaking itself into existence. They carry a unique, random pattern, a chaotic hiss that would imprint itself on the oldest light in the universe. Detecting this signal is the ultimate goal for many cosmologists, for it would be the most direct evidence we could ever obtain for the theory of inflation. It would be like finding a fossil from the first second of time, a snapshot of the universe in its infancy. The challenge, however, is immense. These primordial waves are predicted to have extremely long wavelengths, far longer than what ground-based detectors like LIGO can sense. They have been stretched and diluted by the expansion of the universe itself, fading into a near-silent hum. To find them, scientists look for their indirect signature in the cosmic microwave background, the afterglow of the Big Bang. As these ancient gravitational waves passed through the hot, dense plasma of the early universe, they would have subtly polarized the light, leaving a distinct swirling pattern known as a B-mode polarization. Finding this specific fingerprint in the sky is like finding a single, faded watermark on a document from the dawn of time. While tentative claims have been made, a definitive detection remains elusive, one of the greatest prizes in modern science. To finally confirm the existence of primordial gravitational waves would do more than just validate a theory. It would open a window to a time before the first stars, before the first atoms, allowing us to probe the very moment of creation and answer the most profound question of all: how did the universe begin? A star's final form is dictated by a single critical number. For a white dwarf, the glowing ember left after a sun-like star dies. That number is the Chandrasekhar limit. This is the ultimate weight limit for stability, approximately 1.4 times the mass of our Sun. A white dwarf supports itself through a quantum mechanical pressure, a force generated by electrons being packed together. But this pressure has its breaking point. If a white dwarf gains even a little more mass, pushing it over the Chandrasekhar limit, this delicate balance shatters. The electron pressure is overwhelmed by the crushing force of gravity, and the star collapses catastrophically. This collapse can forge a neutron star or, for the heaviest cases, trigger a complete collapse into a black hole. But how does a dead star gain mass? Often it has a partner. In a binary system, two white dwarfs can orbit each other for billions of years. As they circle, they radiate energy away in the form of gravitational waves. This slow, steady loss of energy causes their orbits to decay, pulling them closer and closer in a cosmic spiral that can last for eons. Their final merger is a spectacular event. If the combined mass of the two white dwarfs exceeds the Chandrasekhar limit, the result is one of the most important explosions in the universe, a Type Ia supernova. This titanic detonation is so uniform and so incredibly bright that it can outshine an entire galaxy, serving as a standard candle for measuring vast cosmic distances. The gravitational waves emitted in the final moments before this merger would be a clear, high-frequency chirp, a direct signal of this impending doom. While quieter than a black hole collision, these waves would carry the unique signature of this specific type of stellar death spiral. Beyond the light and the waves, these supernovae are the universe's primary forges of iron. Every atom of iron in your blood, every piece of steel on Earth, was likely born in the heart of such a cataclysm. The supernova blast scatters these newly forged elements across interstellar space, seeding clouds of gas and dust with the raw materials for rocky planets and ultimately for life itself. The faint gravitational chirp of merging white dwarfs is therefore more than just a signal of stellar death. It is a precursor to cosmic creation. But our ears on the ground can only hear a fraction of the cosmic symphony. To listen to the deepest bass notes of the universe, we must launch our instruments into the quiet of space. This is the goal of a future mission known as the Laser Interferometer Space Antenna, or LISA. Imagine a constellation of three identical spacecraft flying in a perfect triangular formation millions of kilometers apart, with laser beams connecting them like the strings of a cosmic violin. This giant triangle will orbit the Sun, creating the most sensitive gravitational wave observatory ever conceived. In the vacuum of space, free from the constant rumble of Earth's seismic noise and the limitations of a fixed arm length, LISA will open an entirely new window on the cosmos. It will tune into the low-frequency gravitational waves that are completely inaccessible to ground-based detectors like LIGO. What will it hear? It will listen to the stately, million-year-long dance of supermassive black hole binaries, pairs of giants with the mass of billions of suns, as they slowly spiral toward collision in the hearts of distant galaxies. These events are too massive and too slow to be heard from Earth, but for LISA, they will be a dominant, rumbling chorus. Even more exotic are the events known as extreme mass ratio inspirals. Picture a stellar mass black hole, a mere few dozen times the mass of our Sun, captured by the gravity of a supermassive black hole. The smaller object will spiral inward over thousands of orbits, tracing a complex path through the warped spacetime around its colossal partner. This slow, intricate death spiral generates a rich, rising hum of low-frequency gravitational waves, a signal that will allow scientists to map the geometry of spacetime around the supermassive black hole with unparalleled precision, testing Einstein's theory in its most extreme regime. The technological marvel of LISA lies in its ability to measure minute changes in distance. The challenge is to maintain near-perfect free fall for the spacecraft, allowing them to serve as the end points for the laser beams. Inside each craft, a small, free-floating test mass made of a platinum-gold alloy will be shielded from all external forces except gravity. The lasers will measure the distance between these test masses across millions of kilometers, looking for the telltale stretching and squeezing caused by a passing gravitational wave. The precision required is almost beyond belief, detecting shifts smaller than the diameter of a single atom over a baseline longer than the distance from the Earth to the Moon. This is not merely a bigger LIGO, it is a fundamental leap in our ability to perceive the universe. By complementing the high-pitched chirps heard on Earth with the low-frequency rumbles heard from space, LISA will complete our gravitational sense of hearing, transforming a collection of individual sounds into a full, rich symphony of the dynamic cosmos. Gravitational waves might be our only chance to hear the quantum whispers of spacetime itself. For decades, physics has been split into two magnificent but incompatible kingdoms. On one side stands general relativity, which beautifully describes gravity as the curvature of spacetime on cosmic scales. On the other side is quantum mechanics, the wildly successful rules governing the subatomic world. The problem is they refuse to speak the same language. Unifying them into a single theory of quantum gravity is perhaps the greatest unsolved puzzle in all of science. This is where the most extreme gravitational wave signals could become our universal translator. When we listen to the ring down of a newly formed black hole, we are not just testing Einstein's theory, we are probing the very edge of known physics. Some of the most intriguing ideas suggest that spacetime may not be fundamental, but instead emerge from something deeper, like a hologram where three-dimensional reality is a projection from a two-dimensional surface. If this holographic principle is correct, the quantum information that makes up a black hole could leave a subtle imprint on the gravitational waves it emits. The vibrations might carry faint echoes, tiny deviations from the smooth decay predicted by classical relativity. These echoes could be the signature of a quantum structure at the black hole's horizon, a firewall of energy or a fuzzy boundary where the smooth fabric of spacetime breaks down into its fundamental quantum constituents. Another profound clue lies in black hole entropy, a measure of its hidden information. The no-hair theorem says a black hole is simple, but quantum mechanics insists it must be incredibly complex to store all the information of what fell in. This information has to be stored somewhere, and its quantum nature could subtly affect how a black hole vibrates and settles after a collision. Detecting even a minuscule anomaly in the gravitational wave signal, a slight shift in the frequency or damping rate of the ring down, could be the first experimental hint of quantum gravity at work. We are not just listening for collisions anymore, we are searching for the microscopic grain of spacetime. Every new chirp from the depths of space is more than a cosmic event. It is a data packet from a regime where our current laws of physics break down. The quest to decode these signals is a journey to the final frontier of human understanding, a hunt for the underlying code of reality written in the silent ripples of gravity. The first ever image of a black hole was not a photograph of the object itself, but of its shadow. The Event Horizon Telescope captured this silhouette, a dark void encircled by a fiery ring of light, revealing the point where even light is swallowed by gravity's grip. This historic picture and the chirps of gravitational waves are two sides of the same cosmic coin. One shows us the dark, static architecture of a black hole's edge, while the other lets us hear the violent, dynamic collisions that reshape them. They are completely different senses applied to the same mysterious phenomena. The shadow image shows us the geometry of spacetime warped to its ultimate extreme, a frozen moment in gravity's power. The gravitational waves, in contrast, are the real-time soundtrack of that power in action, the ripples from spacetime being violently shaken. By combining these two views, we gain a Chinese letter perspective on the most intense gravitational environments in the universe. We can test Einstein's general relativity with unprecedented rigor. For instance, the size and shape of the black hole shadow is predicted by the theory. The ring down of a gravitational wave signal tells us the mass and spin of the final black hole. Do these independent measurements agree? Any discrepancy could reveal a crack in our understanding, a hint that gravity behaves differently under such extreme duress. Furthermore, this synergy illuminates the chaotic processes we cannot directly see. The brilliant ring of light in the EHT image comes from superheated gas swirling in an accretion disk and from powerful jets of material launched at near light speed. Gravitational waves are silent on this luminous chaos, but they tell us the precise masses and orbits of the central black holes driving it all. By feeding this gravitational data into models, scientists can better understand how these immense gravitational engines funnel matter into jets and shape their surrounding galaxies. It is the difference between seeing a still image of a spinning top and feeling the vibrations it sends through the floor. Together, they complete the story, turning a mysterious silhouette into a dynamic, roaring engine of creation and destruction. The faintest whisper in the cosmos could tell us how everything began. Primordial gravitational waves, generated during the universe's first split second of existence, would have left a permanent scar on the oldest light we can see. This light is the cosmic microwave background, a fossil glow from when the universe was just 380,000 years old. As those ancient space-time ripples passed through the hot, dense plasma of the infant cosmos, they would have gently squeezed the fabric of reality, creating a very specific pattern in the orientation or polarization of that light. Scientists call this unique fingerprint B-mode polarization. It is a faint, swirling pattern, like a series of delicate curls etched into the sky, a direct imprint of gravitational waves from the dawn of time. Finding this pattern is the ultimate goal of a massive scientific hunt, a search for the first tremors of the Big Bang itself. The challenge is that this signal is incredibly faint, buried under a cacophony of other effects. Our own galaxy's dust emits polarized light that can mimic the signal perfectly. Even the gravitational lensing of the cosmic microwave background by later cosmic structures creates its own B-mode pattern, a foreground contamination that must be meticulously subtracted. Distinguishing the true primordial swirl from these imposters requires instruments of breathtaking sensitivity, often placed in the most remote environments on Earth, like the South Pole, where the thin, dry air offers a clearer view of the cosmos. A confirmed detection of these primordial B-modes would be a discovery of Nobel Prize-winning magnitude. It would provide the most compelling evidence yet for cosmic inflation, that brief period of faster-than-light expansion. But its significance goes even further. The strength of the signal directly tells us the energy scale at which inflation occurred. It would reveal the sheer power of the inflationary field, effectively allowing us to weigh the universe at 1/1,000,000,000 of a trillionth of a second old. This single observation would catapult our understanding from theory into measured fact, opening a window to physics at energies so high we can never hope to reproduce them in a laboratory. It is the closest we could ever come to witnessing the moment of creation. These silent cosmic chirps are not identified by human ears alone. Before the first gravitational wave was ever detected, scientists had to predict its exact shape, a task so complex it requires some of the most powerful supercomputers on Earth. This field is known as numerical relativity, and it is the digital engine that makes gravitational wave astronomy possible. The problem is that Einstein's equations of general relativity are incredibly difficult to solve for the most violent events. They are a tangled web of interconnected formulas that describe how matter and energy warp spacetime, and how that warped spacetime in turn guides the motion of matter. When two black holes spiral toward collision, their gravitational fields become so intensely intertwined that the mathematics breaks down. Pen and paper calculations are utterly insufficient. The only way to see what happens is to simulate the entire cataclysm, step by infinitesimal step, inside a virtual universe. Researchers feed the initial conditions, like the masses and spins of two black holes, into a supercomputer. The machine then divides the surrounding spacetime into a four-dimensional grid with billions of points. At each point, it solves Einstein's equations, calculating how the geometry of space evolves over time. It is a monumental computational task that can take weeks, even for a single simulation. The final output is a movie of the entire merger, from the final orbits to the violent collision and the eventual ring-down of the new black hole. Most importantly, it produces the precise gravitational waveform, the theoretical chirp that such an event would create. These simulated waveforms become the templates that our detectors search for. When LIGO data analysts sift through the constant noise, they are not listening for just any odd sound. They are comparing the live data against a vast library of millions of these pre-computed templates, looking for a match. It is like having a cosmic fingerprint database. When a signal is found, the best matching template immediately tells us the properties of the source, its masses, spins, and distance with astonishing accuracy. This entire endeavor is a triumph of interdisciplinary collaboration. Physicists define the problem, mathematicians devise the sophisticated algorithms to solve the equations on a discrete grid, and computer scientists write the code to run efficiently on machines with hundreds of thousands of processors. Without these digital rehearsals of cosmic violence, the real signals from the depths of space would simply be meaningless static lost in the noise. One of the universe's greatest mysteries might be solved by its quietest whispers. Dark matter, the invisible substance that makes up most of the universe's mass, has eluded every direct search, yet gravitational waves could offer our first tangible clue. A compelling theory suggests that dark matter is not made of exotic particles, but of ancient, small black holes forged in the universe's first second. These primordial black holes would be cosmic ghosts drifting unseen through galaxies. When two of them eventually collide, they would create the same distinctive gravitational wave chirp that LIGO and Virgo have already heard from larger black holes. Every merger signal we detect is therefore more than just a cosmic crash. It is a census of the dark, invisible population of the cosmos. The absence of certain signals is just as telling as their presence. The number of small black hole mergers we have observed so far already places tight constraints on how much of the dark matter could be made of these objects. If they were as common as dark matter seems to be, our detectors would be hearing a constant, deafening chorus of collisions. The relative quiet we observe tells us that while some dark matter could be primordial black holes, they cannot be the whole story. Future observatories like the space-based LISA mission will listen for the mergers of even smaller and more ancient black holes, probing mass ranges that are completely invisible to current technology. A detection in that low-frequency window would be revolutionary, potentially identifying the long-sought constituents of dark matter not with a flash of light, but with a subtle ripple in spacetime. This is the unique power of gravitational wave astronomy. It allows us to probe the dark universe by feeling its vibrations, listening for the collisions of objects that emit no light and cast no shadow, yet whose gravity shapes everything we see. Our ability to detect these ripples rests upon a cascade of cosmic coincidences. This leads us to a profound philosophical question known as the anthropic principle. In its simplest form, it asks if the universe's fundamental constants, the very rules of physics, are somehow fine-tuned to allow for the existence of observers like us. Consider the nature of gravitational waves themselves. What if they were significantly stronger or traveled at a different speed? The delicate processes of planetary formation and the stable orbits of solar systems rely on a gentle, predictable gravitational hand. A universe constantly racked by violent spacetime tsunamis would likely tear apart fledgling planetary disks long before life could ever emerge. The very rate of these cataclysmic events is a critical factor. If black holes and neutron stars merge too frequently, the resulting blasts of radiation and gravitational shocks would sterilize entire galaxies, making them uninhabitable deserts. If these collisions were too rare, however, the universe would lack the cosmic forges that create heavy elements like gold and platinum, the very building blocks of rocky planets and complex chemistry. We find ourselves in a cosmic sweet spot, a universe violent enough to create the necessary ingredients for life, yet calm enough to allow those ingredients to simmer and evolve over billions of years. The fact that we exist at the precise technological moment to build instruments sensitive enough to hear these whispers is another remarkable alignment. It invites us to wonder, are we simply lucky beneficiaries of a vast and random cosmos? Or does our ability to listen hint at a deeper connection between the observer and the observed universe? Even the silent fade of a gravitational wave might not be the final word. Some scientists now listen intently for what comes after the main event, a faint, repeating tremor they call an echo. This controversial idea suggests that our current picture of a black hole, with its perfectly smooth event horizon, might be incomplete. The theory proposes that the violent ring-down of a newborn black hole does not just fade into silence. Instead, the waves might bounce against a quantum structure just outside the horizon, a potential firewall or a fuzzy boundary where spacetime itself breaks down. Each bounce would produce a faint, delayed copy of the original signal, a series of ever-quieter echoes following the main crash. It is like listening to a bell toll in a vast, complex cathedral, hearing not just the initial strike but also the subtle reverberations from the walls and arches. Finding such an echo would be a direct challenge to Einstein's classical general relativity, which predicts a clean, echo-less fade. It would be our first experimental hint that the event horizon is not a simple point of no return, but has a physical structure governed by the laws of quantum mechanics. The search for these echoes, however, is mired in a fierce scientific debate. The signals are incredibly faint, buried deep within the noise of our detectors. Researchers use sophisticated statistical methods to comb through the data from events like the first black hole merger, looking for any repeating pattern that stands out from the random background static. Some teams have published analyses claiming tentative evidence for these echoes, while others have scrutinized the same data and found no such sign, arguing that the proposed signals are just statistical flukes. This back and forth is the very engine of scientific progress. It pushes analysts to refine their methods and demands more sensitive observations. The true test will come not from re-examining old data, but from future detections. As our observatories become more advanced, catching louder and clearer signals from black hole collisions, we will have a much better chance to either confirm or rule out these quantum whispers. A definitive detection would rip open a new chapter in physics, forcing us to rewrite our understanding of the most extreme environments in the cosmos, and finally bridging the gap between the vast scale of gravity and the tiny world of the quantum. A black hole could be cloaked in a ghostly fog of particles we have never seen. This theoretical shroud is known as an action cloud. It forms through a process called superradiance, where a spinning black hole acts like a cosmic rotor, stealing rotational energy from the black hole itself and transferring it into a swirling, invisible halo of these hypothetical particles. This cloud does not just linger, it oscillates, vibrating at a specific, pure frequency. And those vibrations generate a continuous, faint stream of gravitational waves, a near-constant hum that is fundamentally different from the sudden chirp of a merger. The signal would be a single, unwavering tone, a cosmic tuning fork ringing for years or even centuries. Its frequency is directly tied to the mass of the action particle itself, a whisper that could reveal the identity of one of the universe's most sought-after constituents. These actions are a prime candidate for the mysterious dark matter that binds galaxies together. Their detection would not only solve that cosmic riddle, but also punch a hole right through the standard model of particle physics, pointing toward a grander, more complete theory of the universe's fundamental forces. This creates a remarkable synergy. Giant underground laboratories hunt for actions by watching for their subtle influence on ordinary matter, while gravitational wave observatories listen for their collective hum from light years away. They are two different nets cast into the same dark sea, both hoping to catch the same elusive prize. A single, persistent tone in our detectors could therefore be more than a new astrophysical phenomenon. It would be a direct message from the particle world, a bridge between the cosmos's largest structures and its smallest, most hidden ingredients. This single event, the neutron-star merger of 2017, marked a turning point in how we explore the cosmos. It was the dawn of the multi-messenger revolution, a new era where we no longer rely on a single sense to understand the universe. For the first time, we felt the space-time vibrations of a collision, saw its brilliant flash of light across every wavelength, and even detected the faint, ghostly neutrinos that streamed from the explosion. This coordinated effort, using every tool at our disposal, transformed a distant chirp into a rich, multidimensional story. From the gravitational waves alone, we knew the masses of the neutron stars and the nature of their final dance. But the light told us so much more. It revealed the fiery aftermath, a kilonova glowing with the newly forged heavy elements like gold and platinum. It showed us the powerful jets of material launched at nearly the speed of light. Each messenger particle brought a different chapter of the same epic tale. This approach is fundamentally reshaping astrophysics. It is the difference between hearing about a car crash from a single witness and having a full accident report with photos, video, and sensor data. The convergence of signals allows for cross-checking and confirmation on an unprecedented scale. We can now measure the expansion rate of the universe with gravitational wave standard sirens and verify it with the observed light from the host galaxy. We can probe the fundamental laws of physics by comparing the speed of gravity to the speed of light with incredible precision. Every time our gravitational wave detectors sense a new ripple, telescopes around the world and in space immediately swivel to the calculated coordinates, hoping to catch a glimmer of light or a burst of particles. This collaborative hunt is turning isolated discoveries into a unified narrative of cosmic evolution, where gravity, light, and matter together reveal the full, spectacular drama of the universe. The silent drain of gravitational wave energy could be shaping the ultimate destiny of the cosmos itself. Every time a pair of orbiting black holes or neutron stars spirals closer, they are not just losing orbital energy, they are contributing to a vast cosmic dissipation. Over trillions of years, as stars burn out and galaxies grow dark, this relentless process will continue. Binary systems across the universe will slowly decay, their orbits tightening as their energy is radiated away into the void in the form of these faint ripples. This represents a fundamental one-way flow, a slow but steady leakage of usable energy from the organized motion of massive bodies into the form of these ever-expanding, ever-fainter spacetime vibrations. It is a process that contributes to the heat death of the universe, a theoretical end state where no energy gradients remain and no further work can be done. The universe would be a cold, dark, and silent sea of uniformly distributed particles, with only the faintest, lowest frequency gravitational waves still echoing from collisions that happened eons ago. Could these waves hold a more active role in the cosmos's grand narrative? Some speculative models suggest they might even be linked to the mystery of dark energy. What if the energy carried away by gravitational waves does not simply dissipate, but instead contributes to the very fabric of spacetime, subtly influencing the rate of cosmic expansion? While this remains a highly theoretical idea, it forces us to consider gravity not just as a force that pulls things together, but as a dynamic player in the universe's long-term budget of energy and expansion. This shifts our perspective on every chirp we hear. Each one is not just a momentary cataclysm, but a small, permanent withdrawal from the universe's finite store of dynamic energy, a quiet step in the billion-year-long march toward an uncertain and profoundly silent future. This cosmic search for whispers is not confined to professional scientists alone. Anyone with a computer and an internet connection can join the hunt, becoming part of a global team of citizen scientists. Projects like Einstein at Home harness the spare processing power of thousands of personal computers around the world, creating a virtual supercomputer dedicated to sifting through the mountains of data from LIGO and other observatories. While you sleep or work, your computer can be analyzing faint signals, searching for the telltale chirp of a distant neutron star or the continuous hum of a pulsar. This is not a symbolic gesture. Volunteers have made genuine discoveries, identifying previously unknown pulsars and helping to rule out noise in the data, which is just as crucial for finding the real signals. This distributed computing model allows researchers to perform analyses that would be impossible with their own limited resources, turning a global network of home computers into one of the most powerful research tools on the planet. But the contribution goes beyond raw number crunching. By engaging with the data, even in a simplified form, people gain a direct connection to the frontier of knowledge. They are not just learning about science, they are actively doing it, participating in a grand human endeavor to understand the universe. This public engagement is vital for the future of discovery. It demystifies complex research and builds a foundation of support and wonder, inspiring the next generation of engineers, physicists, and curious minds. The next great cosmic chirp might not be found in a sterile lab, but on a laptop in a living room, a quiet testament to the power of collective curiosity. These cosmic ripples have already made their way from physics papers to the silver screen. In science fiction, gravitational waves are often depicted as a cosmic weapon or a gateway for faster-than-light travel. A spaceship might harness them to create a warp bubble, or a villain might use a wave generator to tear planets apart. These stories take a kernel of scientific truth and stretch it to its dramatic limits, imagining effects that are instantly visible and destructively powerful. The reality is far more subtle, yet in many ways more profound. A real gravitational wave passing through the Earth would not shatter mountains or flip over cities. Its effect is an almost imperceptible stretching and squeezing of space itself, a distortion thousands of times smaller than the nucleus of an atom. Fiction gives us tsunamis in space-time, while science offers the faintest of whispers. This creative exaggeration serves a wonderful purpose, though. It sparks public imagination and makes an esoteric concept thrilling and accessible. When you see a film where gravity waves are weaponized, you are engaging with the idea that space is a dynamic fabric, a central truth of Einstein's universe. These stories get the basic premise right, even if they amplify the consequences to an impossible volume. They introduce millions to the notion that gravity is not just a force, but a wave capable of carrying information across the cosmos. By separating the cinematic spectacle from the scientific detection, we can appreciate both the creative vision of storytellers and the quiet, meticulous work of the researchers who listen for the universe's genuine vibrations. Our current detectors are like the first crude radios, straining to hear the loudest stations in a sea of static. The next generation of observatories, however, will be like high-fidelity sound systems, tuned to hear the entire cosmic symphony in perfect clarity. Projects like the Einstein Telescope and Cosmic Explorer are not mere upgrades, they are revolutionary leaps. Imagine observatories with laser arms 10 times longer than LIGO, or instruments housed deep underground in ultra-quiet tunnels. These designs will boost sensitivity by an order of magnitude, allowing them to hear whispers from the very edge of the observable universe. This means we will detect binary systems much earlier in their death spiral, tracking their orbital decay for hours or even days before the final frantic crash. We will no longer just catch the final scream of a black hole merger, we will eavesdrop on its entire slow-motion conversation. This expanded hearing range will open up entirely new frequencies. Fainter, more elusive sources will come into sharp focus. we could finally hear the faint pop of a solitary supernova from a nearby galaxy, or the steady hum of millions of distant binary white dwarfs, creating the first detailed map of the gravitational wave background. Every new signal will be a data point in a vast cosmic census, revealing the true population of dark objects lurking between the stars. To achieve this, engineers are pushing the boundaries of technology. They are developing new, heavier mirror materials to suppress quantum vibrations, crafting lasers of even greater purity and power, and creating advanced suspension systems that can isolate the test masses from the slightest tremor. The goal is to build a machine so quiet that the dominant noise is no longer from our world, but from the constant quantum jitter of spacetime itself. These future observatories will transform our listening post from a small room with the door cracked open to a grand concert hall, where we can finally sit and appreciate the full, intricate beauty of the universe's silent music. These silent ripples provide one of the most stringent tests of a principle so fundamental we rarely even think to question it. The equivalence principle states, in its simplest form, that all objects fall at the same rate, regardless of their mass or composition. A feather and a hammer dropped in a vacuum will hit the ground at the exact same time. Einstein elevated this idea into the core of his theory, suggesting that gravity is not a force in the traditional sense, but a curvature of spacetime that affects everything equally. But what happens when the fabric of spacetime itself is vibrating? A passing gravitational wave creates a temporary, oscillating gravitational field. According to the equivalence principle, this wave should stretch and squeeze every object in its path in exactly the same way. A block of lead and a cloud of hydrogen, despite their vastly different internal structures, should respond identically to the wave's pull. This is not just a theoretical curiosity. We can test it with incredible precision by observing the cosmos itself, using natural laboratories provided by pulsars. When a pulsar and another neutron star orbit each other, their incredibly stable pulses act as a perfect clock, tracking their motion through a warped spacetime. If the equivalence principle were violated, if the pulsar and its companion responded differently to the gravitational influence of our own Milky Way galaxy, their orbital timing would show a subtle, telltale drift. After decades of monitoring, no such drift has been found. The principle holds to an astonishing accuracy of 1 part in a million billion. This profound level of confirmation, achieved by watching the dance of dead stars, reinforces that gravity is a geometric actor on the stage of spacetime. Any detected violation would have been a scientific earthquake. It could have meant the discovery of a fifth fundamental force, one that couples differently to various materials. It might have hinted at extra, hidden dimensions of space through which gravity could subtly leak, altering its apparent strength. The fact that gravitational waves, the most extreme expression of gravity, obey this rule so perfectly is a powerful testament to the elegant simplicity at the heart of Einstein's universe. Every chirp we hear is not just a message about a collision, but a reaffirmation of a principle that governs the fall of an apple and the orbit of a galaxy. The death of a truly colossal star is a spectacle that dwarfs even a typical supernova. These events, known as hypernova, are the most powerful stellar explosions in the universe, often linked to the brilliant flashes of long gamma-ray bursts. Their cataclysmic end is not just a simple collapse, but a violent, asymmetric engine of destruction capable of shaking spacetime with incredible force. At the heart of a hypernova is a rapidly spinning, massive star whose core collapses directly into a black hole. Unlike a slower collapse, this rapid birth is fueled by extreme rotation. As the core implodes, it doesn't just form a quiet singularity, it activates a cosmic powerhouse. Twin jets of plasma and radiation, hotter and more focused than anything else we know, are blasted outward from the poles at nearly the speed of light. These jets drill their way through the outer layers of the dying star, and it is this process, this violent, lopsided eruption, that acts like a colossal hammer striking the fabric of spacetime. The sheer acceleration of such immense mass, combined with the dramatic asymmetry of the jet formation, creates a powerful, complex burst of gravitational waves. It would not be the clean chirp of a binary merger, but a louder, more chaotic stutter, a signal screaming of a star being torn apart from the inside out by its own newborn black hole. Detecting this specific gravitational fingerprint is a primary goal for next-generation observatories. Current detectors like LIGO might be able to hear a hypernova if one occurred in our galactic neighborhood, but the advanced sensitivity of the Einstein telescope or cosmic explorer would bring these events into regular view. What would we learn from such a detection? We would finally witness the inner workings of the gamma-ray burst engine itself. The gravitational wave signal would encode the details of the black hole's birth spin and the dynamics of the jet formation, revealing the precise mechanisms that turn a dying star into the universe's most powerful cosmic blowtorch. Each hypernova burst would be a direct transmission from the moment a stellar giant becomes a monster, giving us a front-row seat to the violent birth of a black hole and the brilliant, destructive fire that announces its arrival to the cosmos. One of the deepest puzzles in physics asks if the universe forgets. This is the black hole information paradox, a challenge that pits Einstein's general relativity against the quantum laws that govern the subatomic world. According to Einstein, a black hole is defined only by its mass, spin, and charge. If you throw a grand piano, a library of books, or a cloud of radioactive waste into one, the black hole would respond identically, becoming just slightly more massive. All the intricate information about what fell in, the specific arrangement of atoms and the stories they tell, seems to be permanently erased from our universe. This violates a sacred principle of quantum mechanics, which states that information can never be truly lost, only scrambled. It is the ultimate cosmic conflict between the smooth, geometric world of gravity and the definite, preserved history of the quantum realm. Gravitational waves are now our most powerful tool to probe this mystery. When two black holes collide and we listen to their ring-down, we are essentially taking the fingerprint of the final object. Does it perfectly match the predictions for a simple, hairless black hole of that specific mass and spin, as Einstein's theory insists, or are there tiny, subtle deviations in the signal, faint whispers that hint at something more? Those whispers could be the echo of the information that was supposed to be lost. Perhaps the event horizon has a quantum structure, a vast storage unit that encodes the history of everything that ever fell in. When the black hole vibrates after a merger, this complex information could leave a tiny, barely perceptible imprint on the gravitational waves it emits, a correction to the pure tone predicted by classical physics. Detecting such an anomaly would be a revolution. It would mean that black holes are not the ultimate shredders we thought they were. Information is not destroyed, but perhaps transformed and preserved in a way we do not yet understand, written into the very fabric of the horizon and revealed in its gravitational tremors. Solving the paradox would do more than just reconcile two theories. It would answer a profound philosophical question about our reality, confirming that the universe at its most fundamental level never truly forgets a single detail. The vast cosmic web is thought to connect all galaxies with invisible threads of dark matter. Could the faintest gravitational whispers one day trace this hidden architecture of the universe? This ambitious idea suggests that space-time ripples might eventually map the largest structures in existence. The method would not rely on a single, loud chirp, but on the collective murmur of countless unresolved sources. Imagine listening to a dense forest from a great distance. You cannot hear individual leaves rustling, but the combined sound gives you a sense of the forest's overall shape and density. Similarly, a future network of incredibly sensitive detectors could analyze the statistical patterns in a sea of gravitational wave signals. the subtle correlations between them, the way their amplitudes and frequencies cluster, would not be random. These patterns would be sculpted by the gravitational lenses they pass through on their long journeys across the cosmos. As these waves travel for billions of years, their paths are bent and focused by the massive filaments and dense nodes of the cosmic web. By studying how the waves from different directions are subtly distorted, we could, in theory, reconstruct a three-dimensional map of the dark matter distribution that shaped their journey. The primary challenge is one of overwhelming scale and faintness. The cosmic web operates on scales of hundreds of millions of light years, and its gravitational influence on passing waves is incredibly subtle. Our current observatories are deaf to this specific, diffuse signal. It would require a future generation of space-based detectors, perhaps with arm lengths spanning the entire inner solar system, working in concert for decades. They would need to gather a vast catalog of events, building up a statistical picture so clear that the shadowy outline of the web begins to emerge from the noise. The long-term potential, however, is staggering. This would be a direct way to see the unseen skeleton of the cosmos, to trace the dark matter filaments that have guided the growth of galaxies since the beginning of time. It would transform gravitational wave astronomy from a study of individual cataclysms into a cosmological tool for charting the universe itself. The silent cosmos might be hiding objects stranger than any black hole. Beyond the familiar singularities, theoretical physics imagines a menagerie of exotic compact objects. Picture a boson star, a gigantic, swirling sphere not made of atoms, but of billions of ultra-light particles all occupying the same quantum state, glowing with a faint, ghostly light. Or consider a gravistar, a hypothetical body with a core of mysterious dark energy, encased in a thin, rigid shell of ordinary matter. These are not science fiction, but serious candidates for what might truly lie at the heart of dark, massive objects. Their existence would challenge our very definition of a black hole. How could we possibly tell them apart from billions of light years away? The answer is written in the subtle details of their gravitational wave chirp. When two black holes merge, the final ringdown is a clean, rapid fade into silence, perfectly described by Einstein's equations for a pure event horizon. But a merger involving exotic objects would tell a different story. A collision of two boson stars might not produce a sharp ringdown at all. Instead, their waveforms could show repeated bounces as the stars pass through each other before finally settling or dispersing. A gravistar with its rigid surface would lack a true event horizon. Matter and energy could, in theory, bounce off its interior. In a merger, this could create a series of faint echoes following the main crash, like a bell being struck multiple times. Even a stable wormhole, a tunnel through space-time, would have a unique signature. Its gravitational waves might carry an extra set of frequencies, a harmonic fingerprint from vibrations echoing through its phantom tunnel. Detecting any deviation from the classic black hole signal would be a monumental discovery. It would mean that nature has found a way to create stable, ultra-dense objects without crushing matter into an infinitely small point. Finding a boson star would be the first direct evidence for a new, fundamental field permeating the cosmos. Proving a gravistar exists would provide a stunning link between the large-scale structure of the universe and the mysterious repulsive force of dark energy. Every new chirp our detectors hear is more than a confirmation of known physics. It is a potential message from an entirely new form of matter, a hidden resident of the dark universe finally announcing itself through the vibrations of spacetime. The faint cosmic chirp is often buried in a storm of terrestrial noise, a chaotic sea of vibrations where human eyes alone would never find it. This is where a new kind of intelligence takes over. Machine learning algorithms are now the silent partners in every discovery, trained on millions of simulated signals to recognize the unique fingerprint of a gravitational wave amidst the cacophony. These are not simple search programs. They are sophisticated neural networks that learn the subtle language of spacetime ripples, distinguishing the clean chirp of a black hole merger from the random rumble of an earthquake or a passing truck. Their greatest power lies in speed and precision. In the critical moments after a potential signal arrives, these systems can analyze the data in near real time, calculating the probability that the event is genuine and estimating its location on the sky with astonishing speed. This rapid analysis is the trigger for the entire multi-messenger astronomy network. It sends out automated alerts to telescopes around the world, giving them the celestial coordinates and a head start to swivel toward the source before its afterglow fades. Without this artificial intelligence, the golden opportunity to witness a neutron star merger in both gravity and light might be lost in the slow deliberation of traditional data processing. Beyond mere detection, machine learning is refining our understanding of the sources themselves. By analyzing the intricate shape of a waveform, these algorithms can estimate the masses and spins of the colliding objects with a precision that often surpasses older methods, extracting every possible drop of information from the silent tremor. This collaboration between astrophysicists and data scientists is forging a new path for discovery, where the most profound secrets of the cosmos are unlocked not just by building bigger telescopes, but by teaching computers to listen with a wisdom we are only beginning to understand. Every gravitational wave carries away a tiny piece of the universe's order. These ripples are more than just messengers of cosmic collisions. They are agents of a fundamental process, increasing the overall disorder or entropy of the cosmos. This ties their existence directly to the one-way direction of time itself, the thermodynamic arrow that dictates why we remember the past but not the future. When two black holes spiral together, their perfectly ordered orbital motion is transformed into the chaotic, outgoing rumble of gravitational radiation. That transformation is a one-way street, a permanent increase in entropy that the universe can never take back. This aligns the gravitational arrow of time, pointing from ordered orbits to disordered waves, with the more familiar arrows we experience, like an ice cube melting in a warm room or a shattered glass that never spontaneously reassembles. Theoretical physicists are now asking a profound question: does gravity itself possess a fundamental arrow of time? Some deep ideas in gravitational physics suggest that the Einstein equations which describe the force are inherently time-symmetric, working just as well backwards as forwards. Yet the universe we observe is clearly not. The emission of gravitational waves might be the key physical process that breaks this symmetry, introducing a preferred direction for time on a cosmic scale. Future observations of these waves could test these ideas. What if we could detect a subtle difference in how a gravitational wave signal is emitted versus how it is absorbed? Such an asymmetry would be a direct fingerprint of time's arrow written into the fabric of spacetime. This leads us to a humbling reflection on the nature of our reality. The same faint chirp that tells us of black holes colliding a billion years ago also confirms that time has a direction, a flow from order to disorder that is woven into the most fundamental forces of nature. It suggests that the relentless forward march of time, the very thing that structures our lives and our memories, is not just a local phenomenon, but a cosmic imperative, driven in part by the silent, irreversible whispers of gravitational waves. A century after Einstein's prediction, the faint chirp of colliding black holes resonated far beyond the physics community. It ignited the public imagination, transforming an esoteric concept into a shared human achievement. This discovery did not remain confined to scientific journals. It inspired symphonies where composers translated the waveforms of cosmic collisions into haunting musical scores. Visual artists created installations with rippling fabrics and shimmering lights, attempting to give form to the invisible warping of spacetime. The story of LIGO, decades-long struggle and ultimate triumph, became a narrative of perseverance, a testament to what humanity can accomplish through curiosity and collaboration. In 2017, the Nobel Prize in Physics was awarded to three key architects of the detection: Rainer Weiss, Barry Barish, and Kip Thorne, cementing the achievement in history and bringing the names of these once obscure researchers into the global spotlight. Media coverage played a crucial role, with headlines announcing that we could now hear the universe. Documentaries and news features demystified the science, turning complex interferometers and spacetime curvature into relatable stories of exploration. Social media buzzed with the sound of the chirp, a clip that made an abstract cosmic event tangible for millions. This cultural moment underscored a profound truth: that the quest to understand the cosmos is not a niche pursuit, but a fundamental part of our shared story. The ripple effect of this single discovery continues to inspire new generations of students, artists, and dreamers, reminding us that the most silent vibrations can create the loudest echoes in the human spirit. Our journey through these 50 facts reveals a cosmos alive with silent vibrations. We have traced these ripples from a theoretical prediction on a blackboard to the direct detection of black holes crashing in the dark. We have seen how they act as cosmic rulers, element forgers, and even potential probes of the universe's first moments. These waves are far more than mere scientific curiosities. They are fundamental keys, unlocking secrets about the nature of gravity, the origin of the elements that compose us, and the ultimate fate of the cosmos itself. Every chirp is a message, a story written in the fabric of reality, waiting to be translated. If this voyage into the heart of spacetime has sparked your own curiosity, your engagement helps these discoveries reach further. Feel free to show your support, subscribe for more journeys to the edge of understanding, and let us know in the comments which of these cosmic facts resonated most deeply with you. Was it the sheer power of a black hole merger, the golden glow of a neutron star collision, or the haunting possibility of echoes from the Big Bang? We are all listeners to this grand cosmic symphony, so until our next adventure, keep looking up and keep listening to the whispers of the